Financial Modeling, Topic 6, Computing Portfolio Value at Risk, or VaR, Random Walk Simulations, Macros and At-Risk Simulations, copyright Lou Gaddis. Good references for material on this topic are Financial Modeling by Simon Benninga, chapters on Value at Risk, Monte Carlo Simulations, and Generating Random Numbers. In this topic, we're going to understand how VaR measures the risk of a portfolio, compute static VaR using formulas and normal distribution functions in Excel. We'll make a Monte Carlo simulation using a macro, and then we'll use an at-risk add-in, all to compute value at risk. We'll also learn how to use macros, namely the for loops and cells object. Value at risk is a measure of how much money you can lose over a certain period of time with a certain confidence interval. So, if you are told that your 95% confidence interval 1 year VaR is $10,000, that means you're 95% confident losses will not exceed $10,000 over 1 year. Graphically, that means that just 95% of the expected values are expected to be a loss less than 10,000, or that 95 confidence interval 1 year VaR means that there's a 5% chance of having losses of $10,000 or more. So it's a one-tail statistic. If your portfolio has a expected return of mu and a standard deviation of sigma, and returns are soon to be normally distributed, the X% confidence interval VaR is given by the following formulas. The X% confidence interval 1 year VaR is minus the portfolio value V times the annualized mean minus Z of X times the annualized standard deviation, where Z of X is a statistic coming from a normal distribution. So for example, if you're looking for a 90% confidence interval VaR, Z of X, Z of 90%, would be equal to 1.28. So drawing from the normal distribution, there's only a 10% chance of having a 1.28 adverse change in a variable, or one-tail change, or if an asset is normally distributed with a mean of mu and a standard deviation of sigma, you'll be confident that 90% of the time you will not have more than a 1.28 standard deviation adverse change. Now those Z's generally take on only 3 values, either a 90, 95, or 99% confidence interval VaR, which means my 95% confidence interval Z is 165, so only 5% of the time would you expect to have a 1.65 standard deviation adverse change. And a 99% confidence interval VaR, your Z is 2.33. So again, my VaR is my negative of my portfolio value times the expected return minus Z standard deviations. And I put the negative there because VaR is usually quoted as a positive number. So even though if I didn't have the negative sign there, this number generally would come out as a negative value or a loss, but we just quote it as a positive number. If you're looking for a T-day X% confidence interval VaR, I would calculate the daily mean, multiply times T days, times my Z standard deviation move, using daily standard deviations, and I would scale my standard deviation by the square root of days. That's using the square root rule for scaling volatilities. Often it's written this way. We are given annual means, but we're looking for a T-day VaR. So we'll take the annual mean, divide by 252, which will be roughly the number of trading days in, say, equity markets. That'll give me a daily mean, multiply times T, minus Z standard deviation. I'll take my annualized standard deviation, divide by the square root of 252, that'll give me a daily standard deviation, and then scale the daily standard deviation by T days. So let's do a simple example. We'll take this data, we'll put it in Excel. So I have correlations between stocks, bonds, and cash. I have estimated volatilities of stocks, bonds, and cash of 16, 8, and 2. Based on my correlations and my volatilities, I compute the covariance matrix of stocks, bonds, and bills, which was covered in an earlier topic. I then can calculate the standard deviation of a portfolio of assets. Say we're going to hold 60% in stocks, 30% in bonds, and 10% in cash. The standard deviation of that portfolio is M-mult transpose WSW to the 1/2 power, meaning it's a matrix operation where I take the transpose of these weights times the covariance matrix and the weights again. The expected return of that portfolio is simply the sum product of the means times the weights. Again, this was covered in our topics of estimating portfolio mean and standard deviation. So here's our expected mean and standard deviation of a portfolio. It's invested 60, 30, 10 in stocks, bonds, and cash. I can then ask, well, how much money can I lose over 5 days with a 95% confidence interval? So I'm going to put some named ranges in here. I'm going to make this V. Well, looks like that's not. Let me go change that name range. Name manager. I'm going to delete this one. And let's make sure this has a named range of V. I'm going to give this a named range of U or UA. We'll make it U. That'll be the annualized mean. And I can look over here and see that I do have that range set up as U. U. This is the annualized standard deviation. I'll give that a named range of SA. This will be T, X, and Z. So I'm going to look for a 5-day 95% confidence interval VaR. Here's my VaR formula, given annualized volatility and mean. And the first thing I want to do is calculate my Z variable. In Excel, that's using the norm S inverse function. So the norm S inverse of 95% is 1.645. So your 95% confidence, you will not have an adverse 1.645 change in a normally distributed variable. And then I can calculate my VaR, which is equal to minus V times my annualized mean divided by 252 to make it daily times 5 days minus my Z times my annualized standard deviation SA divided by the square root of 252. That'll make it a daily standard deviation times the square root of T, which will be 5. That'll make it the 5-day standard deviation. And I get a VaR of 23,356. So if I have a portfolio invested in 60, 30, 10 stocks, bonds, and cash, given these capital market assumptions of correlations, volatilities, and means, that portfolio has an annualized mean of 5.8 and a standard deviation of 10.58. If I assume returns are normally distributed with that mean and that standard deviation, I am 95% confident losses will not exceed 23,356 over 5 days. Or there's a 5% chance that losses will exceed this value. If I want to say a 1-day VaR, say 99% confidence interval, I could say that I'm confident that losses will not exceed 15,270 in 1 day with a 99% confidence interval. If I wanted, say, a 95% 1-year VaR, I can switch that to 252 again, which is roughly the number of trading days in an equity market. And you can see that I would be 95% confident that losses would not exceed 115,981 in 1 year. So that's VaR. It tells you how bad losses could get, or the confidence interval that losses will not exceed that value. Now we're going to do a VaR calculation. It's going to roughly come down to the same value, but we're going to do a simulated VaR. This is sometimes called a formulaic VaR, or formula VaR, or an analytical VaR. It just uses Excel's normal distribution functions to estimate a z. But another way to calculate VaR, which is going to be useful in other applications, is to actually randomly generate portfolio values, then sort them, and then look at, say, the 5% worst or 10% worst, and quote that as a VaR. So to do that, we need a model of asset returns and asset prices. And we're going to use a random walk model, or sometimes called geometric Brownian motion model, or random walk model. And this model is very similar to VaR in that it has an expected return component, and it has a noise or shock component. So here it is. Again, it looks a lot like VaR. This says the portfolio value in 1 year, or one period from now, is today's portfolio value times 1 plus the mean, sometimes called the drift. That's the expected appreciation or return, plus a shock of z standard deviations. However, this shock, this z, is not going to be just one value. We're going to randomly generate many z's. All right, so specifically in this formula, this z is normally distributed with a 0 mean and 1 standard deviation. We call that a standard normal variable. So we're going to generate a number of z's. Each time we generate a z, we're going to estimate a portfolio value, an iteration in our simulation, and then we'll sort it, the many iterations, and look at the values. These random generated z's, we're going to use Excel's function norm_s inverse of rand. All right, this is an estimation of trying to create a standard normal random variable z. So therefore, we're going to substitute in Excel the z norm_s inverse rand. So let's go ahead and do that. First of all, I'm going to show you a little about the rand function, the difference between rand and norm_s inverse rand. If I were to just say equals rand, open close paren, you get a random number, and these random numbers are between 0 and 1, and every time I hit, say, the F9 key, I get another value. If I did enough of these, you'd notice that the mean random number for Excel is 0.5 with a min of 0 and a max of 1. All right. When I do a variable that says equals norm_s inverse rand, that is also going to give me random numbers. But these random numbers are different. These random numbers have a mean of 0 and a standard deviation of 1. So if I were to generate, say, 1,000,000 of these random numbers in this cell, G16, I would take the mean, and you'd see it would be 0. If I took the standard deviation of that column, or that series of numbers, it would be 1. So these are the random numbers I'm going to use in my VaR formula. Now the expected value of my portfolio, let's do a 1-year simulated VaR, so I have 252 here and a 95% confidence interval. My expected value would just be my portfolio value, V, times 1 plus the mean. So I expect the portfolio to grow by 5.8%, so I expect the portfolio to be 1,000,058. But when I simulate portfolio values, V times 1 plus the mean again, plus a random shock of z times my standard deviation, SA, I now get a series of, well, in that case, one random number. I hit F9. Now every time I hit F9, I get a random variable, Z. And every time I get a random variable Z, it updates my simulated value. Now if I were to take this value and say copy it every time, copy spatial, copying values, and calculate, say, 1,000,000 of those values, or maybe 10,000 or 5,000 of them, I can then look at the mean. It should turn out to be pretty close to 1,058, but I can say look at the 5% worst case. Take the difference between our current portfolio value and the 5% worst simulated value, and that would be a VaR. Notice every time I hit enter in Excel, say I paste something here, the act of entering a number in Excel generates a recalculation, because recalculation is set right now to automatic. So every time I hit paste, I get a new random number. Now to save us the effort, we're gonna actually copy this number 5,000 times over here. That's going to be a lot of effort. So what we're going to do is we're going to write a quick macro to take this value, which is in the 17th row and 7th column, and I want to copy it over here, then here, then here, then here. So I'm going to write a macro to do that. A macro, or more specifically, precisely in VBA, it's called a subroutine, written sub when you write a macro. So a macro is a subroutine in VBA. It's written by giving it a name and then having no parameters. So unlike a function, you have no parameters. Like a function, you have executable statements, and you say n sub. So it kind of looks like a function, so if you use the word sub instead of function. Macros are either written or run by going to the Developer tab, macro, we have none now, or hitting Alt F8, or you can attach a macro to an art object, and we'll do that. So here's the macro I'm going to use. It's called SimVar 5000. It uses a simple looping structure. I'm going to do 5,000. I'm going to copy 5,000 of those portfolio values in 17.7 and paste it over to the right. So what this, and I'm also going to do one other routine. I'm going to count down my 5,000 numbers so I can see my progress. So here's a SimVar 5000, no parameters, n sub. For I equal 1 to 5,000, next I, that's my loop. It's going to put in cells 3, 9, third row, 9th column in Excel. It's going to be out here. 5,000 minus I. So the first time it runs it, it's going to be 4,999, then 98, then 97. So it's going to be a countdown. And then each time I goes to 1, it's going to put in the 5th row, 9th column. I'm sorry, 6th row, 9th column, 5 plus 1, 9. What's currently in 17.7. So the cells command is something new. Cells command is how you have macros or functions interact with your spreadsheet. So this macro is going to put in my spreadsheet in row 3, column 9, the number 5,000 minus I. Then it's going to put in my spreadsheet, row 6, column 9, whatever is in cells 17.7. It's going to do next I, set I equal to 2. My countdown goes to 4,998. Then it's going to put in cells 5 plus 2, 7th row, 9th column, what's currently in 17.7. And that 17.7 is updating all the time. So I'm going to copy that. I'm going to go to my Developer tab, Visual Basic, insert a module, and paste. Now I can run that macro by going to Developer Macro, but I'm going to attach it to an art object. So I'm just going to insert just a random art object. And then I'm going to right click on that art object and assign a macro. SimVar 5000. Now when I click on that SimVar 5000, it's going to execute my VBA program. It's going to take over here, it's going to put in the countdown 5000 to 0, and then right below it, it's going to take whatever's in 17.7, which is this value here, 1048, and then put it here, and then here, and then here, and then here. So you can see the functions working. This is the for loop, so I is being set equal to 1, 2, 3, 4, 5, and this value here is 5000 minus I. Every time it pastes the value in Excel, this random number generates a new random Z, which then generates a new portfolio value because of the automatic recalc, and it's continually pasting it down there. When that's done, I'm going to have 5,000 simulated portfolio values, assuming the asset returns are normally distributed with a mean of 5.8 and a standard deviation of 10.58. So these are my 5,000 portfolio values. If I take the average of that column, I get 1,053. If I did enough of these calculations, it should turn out to be 1,058. I guess 5,000 is not enough to get the precise value. And then one thing I'll do is I'm going to sort these numbers here and find the 5% smallest value. Again, these are 5,000. Just make sure it goes from cell 6 to 5,005. So we have 5,000 outcomes here. So what I'm going to do is sort these and get the 5% smallest. 5% of 5,000 would be 250. So I'm going to use Excel's small function now. Excel has small and large functions, and all you do is enter an array. So I put in my array as the first parameter, and then I will ask it, I want the 5% smallest. So I know that I can just type in 0.05 times 5,000. That'll give me 250. So the 5,000th smallest value in this column is 877,000. If I take the difference between my portfolio value and my 5% smallest, I get $120,000, which is very close to my simulated VaR of 115. If I were to run this enough times, I would get on average about 115,981. So this is called a simulated VaR. This is my formula or analytical VaR. The advantage of a simulated VaR is we're going to later use this in later topics to add things to my VaR, like changing portfolio value over time, contributions to a portfolio, and this allows me to do more dynamic modeling of portfolios. This is more good for a static modeling of portfolios where the portfolio value does not change and risk does not change. Over time, we're going to use more of this model. So that's simulated VaR. If I wanted the say 99% or say a 90% VaR, you can see my analytical value is 77,000, and I can change this formula to find the 10% lowest, and it gives me 81,000. So once I have this column of numbers, I can look at the 5% smallest, 1% smallest, and so on. And I just added a histogram here just to give you an idea what this column looks like. This is another earlier simulation I did, and these are the 5,000 values, which you can see appear to be normally distributed because that was the distributional assumption when doing the random walk model. Right, that norm S inverse rand, that creates a normally distributed variable. That's why the outcomes appear to be normally distributed. And what we did is we sliced off the 5% smallest and the 10% smallest and took that from the current portfolio value. All right, last thing we're going to do is we're going to calculate the same value. We'll do a 95% VaR. Change this back to 95% or 5% here. Except this time we're going to use @RISK. @RISK is a Monte Carlo simulation software. It's used in Excel as an add-in. It allows you to run, say, normal distributions, and later we'll talk about other distributions you can use. What you do is, once you have Excel open, you go Launch @RISK from your desktop. When you do that and hit OK, you'll notice that @RISK pops up as a menu. So this is my @RISK add-in. @RISK is a software offered by Palisades. If you'd like a student version, you can pay $50 and they'll give you a student version good for 1 year. Normally the price is about $1,600, or get a free 15-day trial. Be careful though, @RISK is not compatible with Mac operating systems, so you'll need to run it on a Windows computer or run Windows in parallel on a Mac. To create an @RISK simulation, you just need to build a model. So this is my model, portfolio value here. You need to specify a random variable. My random variable will be this standard normal Z. And you need to specify an output for your simulation. And that'll be my portfolio value. So in our spreadsheet, we're going to run a simulation using @RISK. What I'm going to do is I'm going to replace the norm s inverse ran with risk normal 01. This is an @RISK command, so it only works when @RISK is on. And then I need to add an output. I'm going to run 10,000 iterations, 10,000 of these numbers, and then I'll sort them and take a look at my 5% worst and calculate by VaR. So to do that, in @RISK, I can take this norm s inverse ran, replace it with risk normal 01. Now 0 is going to sit in the cell, and if I hit F9, nothing happens because this is not a random number in Excel. Only when I run an @RISK simulation will this number take on 5 or 10,000 values. And then I'll take my output, the cell that I want to look at the distribution of, that is a function of this risk normal 01. I'll click on that. I'll just click on Add Output. All that does is actually adds the one simple statement, risk output, before your formula. So you could have done that yourself. So now we're ready to run a simulation. We're going to do, say, 10,000 iterations, one simulation. Now when I hit Start Simulation, it's going to generate 10,000 random variables, which will then generate 10,000 simulated values. If I click on that cell, simulated value, my output, and then start the simulation, this is a graph of the outcomes. You can see most of the values are about 1,050,000, 1,060,000, which is our mean. I can drag this tail over and put in 5% here, which is already in here, and see the 5% lowest value. Looks like it converted this into millions. This is $884,000. I'm going to take this graph, I'm going to copy it, and paste it here. And if I will notice that 884 is roughly my 5% smallest, using my simulation of the macro. If I take the difference between 884 and my current portfolio of $1 million, I get $116,000. So again, my VaR is the difference between this 5% lowest value and my mean value, 1,058,000. So you can see the mean right here, 1,058,000. And the 5% lowest is 884,000. The VaR is the difference between that outcome and my mean. So that's how we use at risk to estimate VaR. Another advantage of VaR is, let me just click on my output again and bring up the interactive histogram. So I'll click on my output, browse results, and I could do things like, what are the chances that my portfolio is only worth $500,000? Well, looks like it's almost zero. What's the probability my portfolio is worth $800,000? All right, there's only a 0.7 chance that this portfolio that's normally distributed with the assumptions given, that'll be worth less than $800,000 next year. You can also say, look at the probability that portfolio is worth $1.2 million next year. That's about 9%. I can get my 95% confidence interval. So I'm 95% confident value between $850,000 and $1.2 million. I can do a 90% confidence interval. So with this histogram in at risk, you can calculate the probability of any value, or the confidence interval between two values, or you calculate your VaR by making it a one-tailed test and getting, say, a 90%. So this will be my 90% VaR, the difference between 1,000,000 and 922. A 1% or 99% VaR would be the difference between 812 and 1,000,000. And that's the difference between the lowest 5% value and the initial portfolio value, not the mean. So that's at risk and how we use it to calculate the risk of a portfolio. So in this topic, we learned how to calculate VaR and what it means. We used a formula and Excel's normal distribution function to calculate it. We used a homemade Monte Carlo simulation, which used a macro that used loops and cells command. And that simulation used a random walk or geometric Brownian motion model of asset returns. And then we used at risk to calculate VaR.